Right, let's see. We'll start first with the preparation of aldehydes and ketones, mostly through problem solving we'll do, okay? Preparation of aldehydes and ketones. See, first is from alkenes. From alkenes, you need to recall how it is done through ozonolysis. So if I take O3 in the presence of zinc and H2O, it will undergo reductive ozonolysis. So that will give us RCHO plus R dash CHO. Okay. We can get aldehydes as well as ketones depending upon how the structure is. So if the structure is like this, and if I do ozonolysis in zinc,
No, పెట్టిన అన్న పెట్టిన
yeah, please keep it on mute, everybody. Yeah. So this will help breaking the bond, make this to be ketone, and, two, and then CHO. This way. Next, if you notice it from alkynes, there are three major reactions here, out of which these two are important. First one, let's say, if we have a unsymmetrical alkyne here and we treat this with HgSO4 and dilute H2SO4, in that case, first a mercury bridge is supposed to be formed, Hg2 plus, like this, and then followed by hydrolysis, that is H2O will attack on the more substituted side, and the bond will break here, making this as OH and Hg plus. Carbon will take away electrons again in the presence of H plus. It will become an enol form, taking H, and Hg2 plus will come out. And this enol form will convert into keto group. That's how we can get keto. Well, on the other hand, if we do this reaction with B2H6 THF and then followed by oxidation, then we will get 3 moles of this group connected to boron. So this is trialkyl boron first. If that is followed by H2O2 in the presence of OH minus, then we will get again enols this way of 3 moles, which on tautomerism will get aldehydes. Right, just like Markovnikov addition in both cases. First case it is following Markovnikov addition. Second case it is following anti-Markovnikov addition. Okay. So wherever you see mercury-based reaction, you remember on triple bond, when it connects, they will give us aldehydes and ketones. Same is the case with B2H6. The alternative reagent for that is Si-A2BH. Okay. Secondary isoamyl boron hydride. Okay. Next, if you check out benzene, third from benzene, we can get ketones as well as aldehydes. First, if you want to get benzaldehyde, so then HCl with CO, if you treat, which we call it as Gatterman-Koch reaction, we will get CHO. Okay. Or we can use HCl plus ZnCl2 in the presence of HCl. That will also give us CHO. okay, or benzene plus CH3, C double bond O, Cl in the presence of AlCl3, it will give Friedel-Crafts acylation, and that's how we will also get this as CH3. Got it? This is from benzene. Okay, how the aldehydes and ketones can be arrived. Okay, first two reactions we have come, quite a number of times already now. So one is Gatterman-Koch, the other one is Koch reaction. Next, see the fourth one now. From alkyl halides, from alkyl halides, we can actually use, geminal dihalides more easily to convert into aldehydes and ketones. Treating that with aqueous NaOH or KOH, it will give two OH groups which will come out as H2O, right? And this will give 2Cl minus. Okay, that's how you can use geminal dihalides. If you have Cl and Cl here, Cl and Cl here in the presence of, you know, uh, DMSO, DMSO, sorry, I'm not required there. So remember for this much only. Next. See the fifth one is from Grignard's reagent. For Grignard's reagent, how do you get aldehydes and ketones? First, any RMGX, if you treat this with, uh, acid chlorides or esters. But if I take only one equivalent, then it will stop at C double bond O and R here, or R dash if at all I keep. Same logic goes for esters also, RC double bond O, RC double bond O, OCH3. If this is how it is, then with one more, we will only get this plus CH3 O minus Mg Br plus. Okay. But if you have Mgx plus not important with number of moles, and I have R dash cyanide here, and then first this R minus will attack on this carbon, and that will make R dash C double bond N minus Mgx plus, and here we'll get this as R. And on hydrolysis, this on hydrolysis will give us R dash C double bond O R plus Mg OH and X. Okay. So basically what you are noticing here, okay, Mg and NH2 here. Basically what you are noticing here is that no matter how many moles of RMGX you use, not one mole, you can use as many moles as possible, but that will convert only up to aldehydes and ketones. Okay. So we cannot expect them to give alcohols. It will not go up to alcohols. Got it? So this is from Grignard's, right? Well, although this reaction is more prominent for carboxylic acid, we need to know this reaction, that is RMGX plus CO2. In case if it is CO2, then R will directly connect it to C double bond O. Then we have O minus Mgx plus, which on hydrolysis will convert into RCOOH. This will be useful going ahead. Okay. Next, sixth one is from alkyl lithium, alkyl lithium. Okay, that is R minus Li plus. Okay, if we treat this with acids, Rc double bond O, OH. First thing, what you'll notice is an acid-base reaction. That is Rc double bond O, O minus Li plus plus RH, R dash and H. Okay. Now, if you take this and react further, if you take this and react further this time, plus R minus Li plus, so this will form RCO minus Li plus O minus Li plus, and then this R minus will attack, correct? And that's how you will get this as RO minus, sorry, plus charges here, O minus and R with Li plus and Li plus. Okay, so this is an complex form. Okay, and further reaction of this will not happen anymore. Okay, so from here, if you do hydrolysis, we will get this as RC double bond O R, right? Plus lithium will come out as Li2O, and that's it. That is the product formation. So you will directly get ketones, but you will not get alcohols in here. So remember, whenever you use RLi with acids, you will end up getting ketones. Okay. Acha, in a separate reaction, if you take ketones and react with R dash Li plus, then alcohols will form. But when you treat with acids, it will only end up getting ketones. Clear? Next. Seventh, from aceto acetic ester, AAE. Okay. Now, basically, here we will have double bond O, OET. This is a procedure, proper, solving procedure. Remember, this is how the question will be given. First, NaOH, then R dash X, then followed by H3O plus, then followed by heat. This is a standard procedure, you know, in which it goes. So remember, wherever, in tree type of questions or anywhere it is coming, this is how it will come. So check what is the first thing we will do. First thing, we will try to remove this H plus, which is which is sufficiently acidic. So we will get a negative charge there, clear? And that is followed by R dash X. So which means this will go and attack on R dash X, forming an SN2 through an SN2 mechanism. We'll get this. And then we are doing hydrolysis. On hydrolysis, we'll get this as RC double bond O. Here it will be OH and R dash. And this is important learning that when you have beta keto acids, you can see this is alpha and this is beta. These are called beta keto acids. Beta keto acids on heating will undergo decarboxylation and you'll get double bond O, R here, right? And this part will be left and H will only be left here and carbon dioxide will come. So this is our final product. I hope all of you understood this point. This is a very standard sequential reaction. So learn how the products are forming, what is the reactant and so on. Okay. This sequence has been asked many, many times in exam. So this sequence based questions, we'll do it right now. Okay. So I hope all of you got a glimpse of it, what it happens. You do it, now you do the questions together with me. So first one, you see, suppose if I give you something like this, double bond O, then I have O like this, O like this. Then I'm treating first with NaNH2. Okay, and followed by Br here and Br here. Here, one more Br I'll put down here. Br and Br here. Again followed by NaNH2 here, and then followed by hydrolysis, and then followed by heat. Okay, try this out quickly, everybody. Check what are the products you will get. Notice the first one. First one, what do we get? First one we get minus here because this is sufficiently acidic. This is a strong base. It extracts proton from here. Later on, that minus will now get connected with any of this position. This minus will go and attack here, removing this Br as an SN2 mechanism. So you can count the number of carbons: one, two, three, four, 5. So there are 5 carbons here like this, CH2, right? 4 times and connected with CH2Br, right? This is what has been formed. And here there is still one more hydrogen. So imagine removing that also, because second time we are making a reaction one more time. So minus here, and internally now this will attack here, remove Br. So that makes a 6-membered ring. So what do we get? Now I'm getting a 6-membered ring. Okay. This one. Now we got a 6-membered ring which is connected to C double bond O this way, like this way, and like this. Double bond O, double bond O. Okay. And then once I get this, I am doing hydrolysis. On hydrolysis, you know that this will undergo, hydrolysis here. So plus 2 moles of ethanol. This is what has been formed. And after that, this product which you get on heating will undergo decarboxylation. Because again, you can see this is alpha, this is beta position. So either you have beta diacids, okay, or beta keto acid or beta diacids. In both cases, you will notice that decarboxylation is observed. So we will get this as COOH plus CO2. Clear, everybody? This is the first product, remember. This is the second product. This is the third product. Clear? Right? Sorry, that is the attack. This is the third product. This is the fourth product, and this is the fifth product. The important hint here, what you need to note is,
Sir,
1 minute, beta. COOH. Even if you have diacids, okay, diacids at beta position, it is called beta diacids. Beta diacids. That also on heating undergoes decarboxylation. We will get this as H and CO2. Just keep this in mind. So you'll be able to solve it. Now, anybody has a doubt, they can ask.
sir, will it be sufficiently negative charge? Will the hydrogen will be sufficiently acidic to get a negative charge, sir, after the alkyl group is getting attached?
Right. As long as you are taking strong bases, then you can always proceed with this reaction, Neeraj. as long as it is NaNH2, H minus, R minus. A lot of time, only these three reagents are used because they are sufficiently strong. You cannot use RO minus, you cannot use OH minus, then those reactions will not take place. Clear?
Yes, sir.
On the same lines, I would like you to do one more question. This, as many times you practice it, is good. Okay, because this will cover your carboxylic acid, ester part, everything as well. Okay, see the next question here. This is second one. First, second one. NaOH followed by CH2 5 times ClBr, okay, followed by NaNH2 followed by hydrolysis and followed by heat. Do that. See in the first case what we can get. First case what we'll get here is double bond O, double bond O this way with minus charge here, followed by attack here. So we will get this as CH2 5 times connected with Cl, and third, this time NaNH2 can extract proton from there and close the ring, makes it a 6-membered ring like this. This is after this procedure. After this procedure, and then on hydrolysis, we get double bond O and acid here, and on heating, we know that acid will go away and ketones will be left. This is the product form. So I hope all of you are able to get that. Any doubt? See the next one. Carbon dioxide with pH Li, right? So first, imagine it this way, that we have O, C double bond O with pH minus, which will attack on carbon. Therefore, what do we get? pH COO minus. Let me write on this way. C double bond O, O minus. Okay. O minus will first take Li plus, Li plus is present here. Then CH3 will attack. So we'll get BHC O minus Li plus, O minus Li plus, and CH3. Okay. Just to give you a hint that nothing more can happen, take this in excess. So even if you take excess, right, further reaction will not happen. This is where it will stop. And then you are making an hydrolysis. So we'll get this as P double bond O CH3. This is after hydrolysis. And NaOI is a reagent for iodoform. So you can notice that iodoform will take place. So we'll get this as pH C double bond O, O minus plus CHI3, a yellow color precipitate. Okay, so this is the final product form. So I suppose all of you got that.
Yes, sir.
Next, let us go further for the preparation where we were studying seventh one. Now, see the eighth one. From 1,3-dithial. 1,3-dithial is when you have sulfur, sulfur connected this way, and this is also a complete sequential reaction where you have NaOH to proceed, following by R dash X. So the procedure how we done earlier, it is exactly same. Again on hydrolysis, what would happen? So here you would notice first, when you have two sulfurs as an ether form at 1,3 position, that will be preparing for a methylene group which is acidic, and that will attack on R dash X. So thereby we will get this as R. Okay. And then when you hydrolyze it, we will get this as SH and SH, and the carbon which is present will be aldehyde. Just to be clear about which type of carbon, we will mark that carbon as an isotopic carbon. So that isotopic carbon remains here, and that will become aldehyde. Okay. So that is how we will get an aldehyde form. Done. Right. Next, see the ninth case, how to prepare. This is from Stephen's reduction. Stephen's reduction. It is specifically for cyanides. So when you have cyanide, pass through SnCl2 in the presence of HCl, followed by hydrolysis. Followed by hydrolysis. So this will give us aldehyde and NH4. Basically, this is how the complex has been formed. Okay. Well, the mechanism is more like, giving away nascent hydrogens here. So this, if you treat with SnCl2 in the presence of HCl, it will give two nascent hydrogens which get added onto uh, carbon as well as nitrogen to get imines. Imines are the intermediates here. So we'll get an imine form. Imine form, when we hydrolyze it, correct, on hydrolysis here. So you think as if H plus is being added, so we will get RCH double bond NH2 plus, right? This is how you get it, which will again convert into RCH2 plus, okay? RCH plus and NH2, okay? Which on hydrolysis, adding water, we'll get this as RCH OH, and this will become NH3 plus. And this lone pair will be pushed, and that's how we will get a product here. Done. So this is a typical reduction here, and whatever the SN, first it will form SnCl2, will take 2 moles of HCl, first it forms SnCl4 2 minus. Again, it will react with another 2 moles of HCl and it will become, lastly, when it becomes, this is the composition issue. Oxidation state here, if you notice, it will change from +2 all the way to +4. Okay, that's how it will get oxidized and carbon is getting reduced. I guess this part is clear, everybody. Right. Next, heating of heating of carboxylic acids. Two cases we already learned through example only. That is first one being beta keto acids. So double bond O, double bond O, OH. And just our room temperature, if you heat, that is sufficient enough for this to convert into keto and give carbon dioxide. Similarly, if you have double bond O, double bond O, OH and OH, beta acids also, that on heating will give you, you know, carboxylic acid plus CO2. Okay. And now, if you have adipic acid, that is, we have CH2 four times, which is connected to UOH and COOH. This is adipic acid. Before adipic acid, when you heat it, right, you will get anhydrides and so on. But from adipic acid onwards, if you notice, you will get, you know, a 5-membered ring and then decarboxylation will happen. So cycloketone will get. Similarly, if you have CH2 5 times with COOH and COOH, that on heating will give cyclohexanone plus CO2 plus H2. So this is the effect you will notice on heating. Okay, here, these questions will be pretty much clubbed with one thing. I mean, if you know it upfront, it will be better. That is, at any point of time, cyanides, right? Cyanides, when you hydrolyze it, will always convert into carboxylic acids. So that becomes a starting point for most of the questions, right? And this will become NH4 plus. And even if you take a basic medium also, like NaOH, it would become RCO minus and NH3. Yeah. Detailed mechanism we could actually search again, discuss again on carboxylic acid. But for now, for solving questions, this part becomes important. Okay. Now, how questions have been framed, let us see on this model, how the questions have been framed. See, first model. This is again a very, very standard question to ask. You have two cyanides here and two cyanides here. So this is like a starting part of the reaction. And from there, H3O plus and followed by heat is been given. So that will give us X. And that when you treat with C6H6 in the presence of AlCl3 will give you Y. And that in the presence of Hi, red phosphorus, right? In excess amount will give us Z. Find X, Y, Z. Everybody understood how the questions are framed in this area? So before getting X, what we should do? Hydrolysis. On hydrolysis, this will become acid, 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 and acid. Okay. So if all of the four will become acid, what do I get? I will get, COOH, COOH, and then COOH and COOH. Obviously, when you have a beta keto acids, the first thing you will do is decarboxylation. Decarboxylation is a relatively easy step. Generally, student ask me, sir, whether we should go for dehydration and make anhydride. First thing you should always prefer is decarboxylation. So if we do decarboxylation, what we shall get here is COOH here, COOH here, and 2 moles of CO2 will be lost. And this will undergo dehydration now, and that will give you anhydride. This is the compound which you get. So this is your compound X. And anhydride, when you treat with benzene, benzene plus anhydride in the presence of AlCl3, so double bond O, double bond O, O. So O will convert into AlCl3 minus plus. This bond will break and benzene will go and attack here. Okay. Hello. Yeah. Right. See, this will attack on this position. So what do we get? Benzene with C double bond O like this. We have group here, and this is connected to carbon, which will become COOH. That's it. This is what you'll get. And this is your Y. Yes, beta. Oh, sorry, there is no benzene. This is what you'll get. And finally, this is getting reduced. So if you reduce that, benzene will not get reduced. Benzene will remain benzene. And here it will get reduced. And you're using excess, so this will become methyl. So this is your compound Z. Anybody has a doubt, they can ask me now. Please check once.
Sir,
Yes, sir.
sir, beta diacids can also undergo decarboxylation, no, sir, on heating.
Beta diacids. Yes, beta.
Then why did we take anhydride, not
That is not beta, no, beta. This is alpha, beta, gamma. Correct. Beta means adjacent to it. Hmm? Let's see the next question. Suppose if I give the starting material like this, double bond O, CN, 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 and CN. This on hydrolysis followed by heat. I will get A, and this A I'm treating with CH3 MgBr of two equivalents only. We are not going for multiple equivalents, only going for two equivalents. And then we are going for CH3Li, okay, CH3Li excess, and then going for hydrolysis. That will give us compound B. Got it? And this followed by copper and heat will give us C. Find ABC. So let us notice first what we can do is convert everything into acids. Double bond O, COOH, 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 HOC, HOC, HOC. Then on heating, you know that we'll get double bond O, right? And here I will get oxide like this and like this. This is the end product we'll have. Why? Notice this. These first one CO2 will come out, this CO2 will come out, this CO2 will come out. This is the first thing. And next, this CO2 will also come out because it is positioned at beta carbon, beta keto position. Because there is a beta keto, so both the CO2 will come out eventually. Here one CO2 and one CO2. And the leftover two carbon dioxides, they are not exactly at the beta position, they are at gamma position, so they form anhydride. So this is your compound A. Now, I am using only two equivalents. Okay. If it is two equivalents, what would I get? So first equivalent will be more reactive to aldehydes. Anhydrides are less reactive than aldehydes and ketones. So first you will get methyl here, O minus, MgBr plus. And next here it will attack, which will give us C double bond O minus, MgBr plus. And here it will attack to get double bond O with one methyl group. This is what you will get. Okay. And later you are also reacting with CH3Li excess. Okay. Now remember CH3Li excess, what will it do? It will react here with one mole. It will react here with one mole. So what is the product you will get? Let me just copy this here. So here we will remove this and we will get one CH3Li. Here we will have CH3. One CH3 will come here and one more CH3 will come here. So we'll get this as O minus and two methyl groups, right? Okay. Basically, it is not completely CH3Li. This is O minus Li plus, and there is one more O minus Li plus. Okay. That will anyway will get hydrolyzed. So I was writing it directly. Here also it is Li plus. And now on hydrolysis, what is the product I'll get? Here is uh, this one methyl and OH here, and then here we will have double bond O and methyl here, and here we'll have again two methyls with OH here. Done. So you can get two tertiary alcohols and one ketone. This is your product B. And copper and heat. Remember what does copper and heat does? Okay, copper and heat will give you a double bond correct? And if it is a double bond, if it is on the what do you say, more substituted side here, double bond on this side with methyl, and here we will get double bond O, right? And on tertiary positions, it will give double bond like this, OH and H will go, and this is what you will get. So this is compound C. It will not disturb any ketones. Ketones, they are already in an oxidized form, so nothing will happen. See, I can make a lot of questions out of it. D, I could use again as a decarboxylation. So I can use NaOI. If it is NaOI, what is the product form? If I take this compound, same thing. Here, iodo form will take place. So here I'll get acid OOC minus plus CHI3. Tertiary alcohols, nothing will happen on iodo form. Yes, all of you understood that. See the next preparation, 11th one. Suppose if you have C double bond O and then there is an acid, that is alpha keto acids. Alpha keto acids. Alpha keto acids also on heating with concentrated H2SO4. On heating with concentrated H2SO4, that will also convert into an acid plus CO plus H2. Well, we'll be learning this again in carboxylic acid. We might require here for application. So first you will remove this carbon dioxide, and um, and then we will get this as an acid. Okay. All right. So if you check out the star carbon here, this is that star carbon which will remain, and this one will come out as CO2. CO gas. Sorry. Again, for now, no mechanism required. So just remember that equation, how it happens. So pH, C double bond O, C double bond O, OH, if at all it is given. Same thing with concentrated HI and heat, we will get pH, COOH plus CO plus H2O. Right. Next, 12th one from dry distillation. Preparation this time from dry distillation. Okay. We can use dry distillation of barium, calcium 2 plus, barium 2 plus, you know, uh, thorium 2 plus, thorium plus 3, strontium, strontium plus 2, and so on. Okay. Now, if you notice that, first, if I take 2 moles of acids and react that with base like calcium hydroxide, then we will get Rc double bond O, O minus, twice calcium 2 plus. And this will undergo dry distillation. Dry distillation. Convert that into Rc double bond O, R plus calcium carbonate. Now, typical examples in this case like HCOO twice calcium plus RCOO twice calcium. If we have mixed salts here on dry distillation and heat, so we will get RC double bond OR, and one is R, this one is self, the other one is cross, RC double bond OH plus H C double bond OH plus calcium carbonate. Okay. Now this is always little debatable whether a formaldehyde is formed or not. But as much as mains questions are concerned, they have always used this as a product as well. So my suggestion is go for this product also. Okay. Although it has been observed that this will decompose into carbon monoxide easily, but since in questions I have noticed that they have been asked, taken this also as a product. So this one is self, and this one is cross. So three products you can make. Clear? Now this question becomes more typical when it is in a cyclic form. Okay, so that kind of examples you should do. See this second example. So where you have four carbons here with double bond O. Okay, sorry, fifth carbon with COO minus, with COO minus, and calcium 2 plus. Now, if this salt has been heated, so what do? We will join one carbon and remove one carbon as calcium carbonate. Simple. That's how you will do it. Okay. So same way, if you have CO minus, CO minus succinic acid and calcium, it is as a part of calcium 2 plus salt. So that will also become cyclopropanone and calcium carbonate. Okay. So using this, again, a lot of questions are framed. So let us try one question here now. This is PYQ only, but old PYQ, how they have been asked, check. If you have COOH here and COOH here, this way, this first he has given as part of heat. First heating is given, which he said that it will give X product, Y product, and Z product. Clear? Y product, Z product here. And out of this one is X is the organic compound, and that X organic compound is treated with zinc, Hg, HCl to give A, and that when you treat with COCl2, okay, sorry, COCl twice in the presence of AlCl3, give compound B. Okay. And this compound B is being treated with lithium aluminum hydride in excess, followed by hydrolysis to give compound C. And this is followed by H plus and heat to give compound D, which is followed by NH2 in the presence of OH minus to give compound E. This is how the question has been framed here. So see what we can do. First one, what we will do is simply make dehydration, because this position of COH will demand for dehydration. So if it is for dehydration, we can say it is double bond O, and one oxygen. So this will bring to a six-member ring. So that's not an issue here. Clear? Oh, no. How many rings we had? 1, 2, 3, 4, 5, 6, 7. Sorry, 7 we have. So decarboxylation will take place. So we will get this as double bond. Okay. So CO2 will come out. So this one is X and Y is CO2 and Z is H2O. Okay. Or either ways. Z could be H2O, Z could be CO2, and Y could be H2O. Now, once you get X here, we are making a reduction out of it. So from there, I can say we will get this compound, which is reduced from Clemenson's reduction. And after that, we are adding COCl by Friedel-Crafts alkylation, acylation. So acylation happens usually at para position. So this is the para position which will have C double bond O. Again, I have C double bond O. So there are two C double bond O's. So that means on both the benzene groups, it will get attached like this. And this is the compound which you will get. And this is compound B. And if I make a reduction out of it, right, which is compound C, so this will undergo reduction to alcohol on both sides. Okay. This will undergo to get a reduction of alcohol form because ketones will convert into alcohols here. Okay. And alcohols here. Yes. And heating is been done once again. So on heating, we will get this compound as dehydration will take place. Dehydration, this is compound C. Then we need to fetch compound D. On dehydration, one OH will go and one H plus will go. That will give us enol like this. And you know that enol is unstable, so it will convert into keto form. So that's why I'm writing directly as a keto form here, double bond O, CH2. And this is compound D. And again, what are we doing? We are reducing with NaNH2, Wolff-Kishner reduction. So this compound will convert into an alkane form. So it will join here and that will become E. Right, please check this out, everybody. Shall I go ahead? See, next one. 13th way to prepare 10, 11, 12, 13th here. 13th way to prepare aldehydes is from acids with MnO4. Acids with, sorry, MnO. So suppose if you have as simple as formic acid, right? And I take 2 moles of formic acid like this with MnO and heat. So you will notice that one will come out as carbon dioxide, the other one will become aldehyde plus CO2 plus H2. And the procedure follows the same thing. If you have RCOOH plus R dash COOH in the presence of MnO and heat, this is exactly like dry distillation only. So we'll get this as RC double bond OR plus R dash C double bond OR R dash plus RC double bond OR dash. Right. These are the three products we get. Same we can see intramolecular, preparation also. Got it? Next. 14th is from,
Sir,
ethyl. Yes, please.
so what is the use of MnO2?
Huh?
So what is the use of MnO2 and the difference between before and this one?
Nothing much difference. It is same thing. Instead of calcium plus 2, now we'll get a salt of manganese.
Okay, sir.
Okay. Ethyl ortho format. From ethyl ortho format. That is RC. Suppose if you have OET, OET, and OET. Okay. This is ethyl ortho format. As a format, if I have written, then it should be H. So this if you react with R dash MgX, okay. So then First thing you will add is R, C, R dash, and then OET, and then we have OET plus ETO minus. Okay. On this, further RMGX cannot be added easily. So that's why if you hydrolyze this, if you hydrolyze this H3O plus and heat, then it will become HC double bond O R dash plus 2 moles of ethanol. Okay, not heat not required, sorry. 2 moles of ethanol you will get. This is the product. Clear? Next.
Sir,
Yes, Vijay.
so what product will we get if we hydrolyze it first
Huh?
without treatment with RMGX?
If you do hydrolysis first you'll get ester. Okay. And then you react with RMGX, you'll get 2 moles to get added. For sorry, 1 mole to get added, you'll get ketone. If not, if you give excess, in that case, it will become alcohol. Okay. So just
Okay, sir.
something is the starting material. Yeah. Next one is Rosenmund's reduction.
So can you explain the mechanism of that?
Which one better? Earlier one.
Yes, sir.
HCOET, OET, and OET. R dash MgX being a strong nucleophile, as it attacks simultaneously OET will remove. So I will get this as OET, OET, and R. Got it? And as soon as I hydrolyze that, the lone pair from here will take H plus, becomes OET, R, and OET with H positive charge. Okay. So the lone pair from here will push so that this group can leave. So we will get this as HC OET double bond plus and OR. And that's when, sorry, not OR, R. That's when water will attack here and remove this. So imagine the H plus is also going on OET. H here plus and OH is present here. So what would happen? Now lone pair of from OH will push to remove this. So that ends getting aldehyde. Clear? Notice Rosenmund's reduction. Rosenmund reduction is mainly done by acid chlorides. This when you treat with H2 palladium barium sulfate in CaCO3, okay, or sulfur sorry CoCO3 in sulfur or quinoline. These are the solvents which are being used. So that will convert into RCHO. Okay. This entire thing, H2PD barium sulfate, is also called as Lindlar's catalyst. Lindlar's catalyst. Okay. Double bond OCl, double bond here. So if we react this with Lindlar's catalyst, what would I get? Double bond OH, ethyl here, double bond here. That's it. This is the product which is formed. 16th is etard reaction. Etard basically is a case when we use it for toluenes. Toluene, when you treat with CrO2Cl2 in the presence of CS2, this will be first step. Second step is to hydrolyze it. That will give us benzaldehyde. Okay. You can do the same thing using, instead of chromyl chloride, I can directly use chromic anhydride also, which is CrO3 in the presence of CH3, CO twice O in the presence of anhydride, CO. Again followed by hydrolysis. Here also I'll get to see formaldehyde form. Mechanism wise, if you notice, just two steps you need to know. That is, where there is an aldehyde, where there is a toluene, at two positions we will have Cr double bond O. This is connected to oxygen via oxygen this way. Oxygen this way, Cr double bond O and Cl and Cl. This is how it is connected. And which on hydrolysis will give you the product. Got it? And this is only applicable for aromatic aldehydes only. We cannot get aryl. Okay, this is only for aromatic aldehydes. Next, 17th is from Gilman's reagents. See, any reagent which is of alkyl metal, right? So this is organometallic compounds. Those are called as Gilman's reagents. RC double bond O Cl. If you take Gilman's reagent, okay, then you will get this as RC double bond O R dash. Now, what are the Gilman's reagents here? Okay. I can take R2 dash, sorry, R dash twice CD, R dash twice R dash and lithium, R dash Li, and R dash twice CuLi, got it, and R dash, that's it. Okay, these are the three cases. In all these three cases, you will get that R dash getting connected there. 18th one is dibal H. We use dibal H for making aldehydes and ketones, right? Acids very rarely reactive. Okay, dibal H followed by hydrolysis. You get RCHO over yield. But it is best for cyanides, best for esters, and best for acid chlorides. And these, when you use dibal H followed by hydrolysis, well, we will get aldehyde. This is the aldehyde you will get. Done. See, there is alternative to dibal H, and alternative to dibal H is alternative to dibal H. Dibal H is Li with Me thrice CO and 4 thrice aluminum hydride. Okay. This entire thing, this is the compound which you have. Okay, so basically it is lithium dirt butoxy aluminum hydride. This works as an alternative, and it is very useful in case of acid chlorides. For acid chlorides, it is most useful. Acid chlorides, if you use This one. Lithium tert butyl hydride. You will get this as RCHO. This is from Daibalage and its alternative. 19th one is Wacker process. Wacker process is when you have RCH, any alkene, when you treat with PDCl2, right, in the presence of O2 and CuCl2, followed by hydrolysis. So you can get this as CH3, R, C double bond O, CH3, plus palladium getting reduced and HCl coming out. Okay. In such cases, you always think as if you're making a, what do you say, Markovnikov addition, simple. So you can think like this, this O2 and H2O is basically making OH minus and H plus. So it is like you will be adding H plus, convert that into ketones. This is Wacker's process. And 20 is oxo process. So when it comes to oxo process, now R CH double bond CH2 in the presence of carbon monoxide plus H2. Okay. Usually it is used in cobalt carbonyl compounds like this, and that will become R CH2 CH2 CHO. Okay. You can notice that it is like you are adding, H minus and HC double bond O plus and make it like in Markovnikov addition. So that means first electrophile will get added, then nucleophile will get added. Then this is a typical mechanism which you can observe. Okay. One PYQ which was asked, let us discuss that on this basis, is this one where you have an ethyl here, which is first treated with Br2H nu, which followed by NBS heat, which is followed by 2 moles of NaNH2 and heat. H2 and heat. Sorry, not 2 moles, 3 moles. 3 moles of NaNH2 followed by H2O and then followed by H2, the presence of palladium, barium sulfate, and that followed by CO plus H2 in the presence of CO4. So this gives a product A. Find A. Check everybody. Yes, Satvik, CO plus HCl is also an oxo process. Yes. No. HCl, Satvik, when you take in oxo process, you should take metal also in that case, so that Cl minus will not come. Okay, H minus will come as a nucleophile. quick. See, what is the product form? First one is going to be one Br here. Second one will also be Br on the same position. So you have two Brs here, and then 3 moles will make an elimination and also create a minus charge, and that will take H plus, making a triple bond here. That with reduction will make it double bond, and if we make an oxo process here, so we'll get 1 2 CHO. This. So this is the product we'll get. Clear, everybody? Right. Now you see what are the chemical reactions we need to check out from aldehydes and ketones. The first most used reactions are NAR, nucleophilic, addition reactions. Nucleophilic addition reactions. Out of that, the first addition we'll see is of HCN. Okay, and directly, these are all something which you can relate quickly, so I'm not taking much time on this. So aldehyde plus HCN, it is always reversible to give R, CH, OH, and CN. This is cyanohydrin. To increase the content, if you, because HCN is a weak acid, generally some amount of casein is already added to initiate the reaction. Okay. Clear? And only small amount should be added here to initiate. Rest of the amount will be taken care by HCl. Okay. All aldehydes and ketones, all aldehydes and ketones give the reaction. Okay. So any form of aldehyde, any form of benzaldehyde forms here, or to that matter, even this kind of ketones as well. Okay, this will be reacted. Correct. Now I want you to anyways read once what happens to the properties of nucleophilic additions. Out of which the reactivity wise, if you notice, reactivity, reactivity of nucleophilic addition reactions. Right? First will be CF3 CHO, very strongly reactive. CCl3 CHO, then CF3 COCF3, very strongly reactive. After that comes aldehyde, then simple aldehyde, that is CH3CHO. Correct. Anything which is slightly getting crowded aldehydes now, like this. And all the types of aldehydes, any type of aldehyde, even for that matter, tert aldehyde, this one is also more reactive. Then you compare to the simple ketones. So, sorry, here I have to write this one, PHCHO, and then comes heavily crowded aldehyde. After that only we will get, simple ketones, and then little bit more substituted ketones like this. And finally, we will have PH double bond O, CH3, and PH double bond OPH. Okay. And this one as well as PH with double bond or tertibutyl. These kind of cases, they will have similar reactivity, rather they will have very, very poor reactivity. So this is how the nucleophilic addition reactions will take place. So be careful with the order. Next. So except this case, right? Except this last two cases are very difficult for any reaction. Rest all the contents which are present here, they all give positive test for cyanohydrin. Okay, so cyanohydrin can be added very easily. Next, second reaction is NaHSO3, NaHSO3 addition, sodium bisulfate acid addition. So in sodium bisulfate addition, if you take any aldehyde, plus SO3 2 minus, correct? Because uh, NaHSO3 will always come out as HSO3 minus, or you can write it as HSO3 minus also. Okay. So as you add that, we will get RCO minus and SO3 minus Na plus and H, which on hydrolysis will give us RCOH, H and SO3 minus Na plus. And this would be a white precipitate. It is a white precipitate. Got it? Now, if you take this one and treat with NaOH in the presence of H2O again, so this will convert back to aldehydes plus SO2 gas will come out plus Na2SO3 will form. Okay, some part of it. If you add it to HCl and H2O and hydrolyze it strongly, on strong hydrolysis again you'll get RCHO SO2 plus NaOH. Sorry, not NaOH, NaCl. Okay, this is the product which you will see. Here, one important aspect about sodium bisulfate is reacts with methyl ketones only. Okay, in some cases, not even methyl ketones. Okay, negative NaHSO3 reactions. That means where the reaction will not happen with NHSO3, you will see is pH C double bond O CH3. Although there is a methyl group here, even this is a methyl group, still will not take place. Anything which is ethyl will not take place at all. This reaction will not happen. And if you have anything bulkier than that, definitely no reaction here, right? And third butyl, definitely no reaction on either side if there is third butyl, correct? In these cases, you will not see any reaction, guys. All right. In rest all cases, all the aldehydes will show. All aldehydes will show this reaction, and simple ketones will show this reaction. Third reaction is from reaction with water. H2O and H plus. Okay. Usually here, what we are expecting is a hydrate formation, that is HCHO in the presence of H plus should form RCH, OH and OH. This is called hydrate of carbonyl. Hydrate of this carbonyl compound. Hydrate of carbonyl. Okay. Which hydrates are stable is the question usually asked. So you can notice stable hydrates. So if you notice stable hydrates, CCl3CHO, this is chloral. Chloral forms a very stable hydrate. Basically, if you pass chloral through H3O plus, then you'll have C, Cl, Cl and Cl, which is connected with C, OH and OH like this and H. And here you will have hydrogen bonding. Here you will have hydrogen bonding. Because of strong hydrogen bonding, this is a very stable hydrate. Okay. Similarly, if you notice that this one is also very stable hydrate, then Ninhydrin is very, very stable hydrate, double bond O, like this. This one is also stable hydrate. Here, this would form OH and OH, which will release the strain. Here, it would form OH and OH, double bond O and double bond O, and forms a stable hydrate by hydrogen bonding between these two. Okay. Then pH, C double bond O, C double bond O, and C double bond O, and pH. Again, on this position, hydrate is very stable. Correct. And if you notice the equilibrium value for these cases, right? So if you take the compound here and the equilibrium value here, in case of ketone, it is very, very less. In case of aldehyde, it is slightly greater. So you would notice that while taking the hydride, if the question is given that which one will have more in the forward direction, then you will take this aldehyde also, simple acetaldehyde. Formaldehyde will anyway give the stable hydrate here, 2280 is its value, and CCl3CHO will give around 2000. And if you have CF3, COCF3, this will make very strong hydrogen bonding from 10 raised to the power of 6. So that will exist only in the hydrate form. Please notice with the hydrates, everybody. I see the next reaction. Fourth reaction is with ammonia, right? And ammonia derivatives. Reactions with ammonia derivatives. Let's explain cyclopropane one. Cyclopropane one is simple beta. Here, because of double bond, it has a lot of strain. It's supposed to maintain 120 degrees bond angle, which is very difficult. But if it becomes a single bond, makes sp3, now it is supposed to maintain 109 degrees. So that means the strain has decreased. So if it becomes sp2 to sp3, strain will always decrease. Correct? See, reaction with ammonia derivatives here. So if you have any aldehyde or a ketone and treat with ammonia at pH, around 4 to 6, not very high or low. So in that case, it will become RCH and NH. These are called imines. Okay. And imines, if there are any substitutes, these are called Schiff bases. Okay. So this is about how the reaction proceeds. But if you notice the same thing, instead of NH3, here we have RNH2. In that case, this will become N and R here. Now these imines are called as Schiff bases. Schiff bases. Okay. Usually, Schiff bases will undergo reduction quite easily. In fact, with all the reducing agents, it will undergo reduction easily to get R, CH2, NH, and R. Okay. What are those reducing agents? Reducing agent can be lithium aluminum hydride, sodium boron hydride, okay, PDC, H, PDC with H2, PDC with H2, nickel with H2 here, ethanol in the presence of sodium or sodium in the presence of ethanol. Okay. And these are all good reducing agents for converting into alkane. And of course, red phosphorus and HI. Right? Achha, I forgot one more. In case if you have zinc, mercury, amalgam also, it will happen. Okay. And NH2, NH2, KOH. Wolff-Kishner or Clemenson's will also make a reduction of this. Okay. Reaction of 2-degree amines is important. Okay. That is where the questions will be asked. Example. Suppose if you have double bond O and I treat this with N H here. So now this is a 2-degree amine. Earlier what I have written is 1-degree amine. So in the presence of H plus, now it will start forming a new type of amine which we call it as ene and amine. So enamine. This is enamine formation. Okay. I hope you guys remember Stokes enamine reaction. Just go through the notes once. Okay. What is Stokes enamine? How it is to be done? Get an idea there. If you have ammonia derivatives, you know how the products are, right? Which case you will get oxime, which case you will get hydrazone, which case you will get, you say, semi-carbazone. Right? I'll just give you that idea. If we have particular Z value here, what is the compound and what is the product? So if you have OH here, it is called hydroxyl amine. The product you will get is oxime. Product you will get is oxime. That is R CH double bond N and OH. Okay. Oximes are colored in general. Oximes are colored in general. Okay. Next, NH2, hydrazine. See hydrazine will become hydrazone. Okay. NH, pH. It is phenyl hydrazine. So that will become phenyl hydrazone. Phenyl hydrazone means we'll have like this R, CH, double bond, N, NH, and pH. Phenyl hydrazone. Okay. If you have NH, right, then we have C double bond O and NH2. From here, if it is getting connected, so this is semi carbazide, it will become semi carbazone, which is RCH double bond uh, N with NH, C double bond of NH2. This is semi carbazide. Last one is important, which is Brady's reagent, which is NO2 here, NO2 here, and NH. This is what is getting connected. So this is 2,4 dinitro, dinitro, phenyl hydrazine, also known as Brady's reagent. So through Brady's reagent, you will get same thing, 2,4 dinitro phenyl hydrozone, also known as 2,4-DNP, 2,4-DNP, and that is RCH double bond NH with this entire group NO2 and NO2. All right, this is Brady's reagent. Next, specific reaction in this case would be, erythropine form. So that is 6 moles of HCHO plus 4 moles of NH3 on heating will give you CH2, 6 moles and N4. This is hexamethyl tetraamine, hexamethyl tetraamine, or also known as urotropine, or urotropine. Okay. Structurally, if you notice, it is like a chair form of it, like this. We have this way, one nitrogen above here, the other one here. Other alternative reactions in this case, right, of a similar kind is when you have, um, you know, hydrazine, for example, PHCHO, PHCHO. When you treat with H2N, hydrogen, and another molecule is C with PHO, CH. So now you think this way, here H2O is lost, and here H2 is lost, and here this H2 is lost on heating. This is H plus and heating. So what do we get here now? So we will get this as PHC double bond N, PHCH double bond N, okay, which is connected to two carbons here, CH and PH. This is the product you will get. Another one is 3 moles of acetaldehyde when you react with 3 moles of ammonia and heat it. It is similar to like an aldol. So where 3 moles will connect with these 3 ammonia groups like this, we will get so NH, NH and NH plus 3 moles of H2. In this case, one more reaction which you will notice is Beckmann's rearrangement. Beckmann's rearrangement where we have R dash C double bond O plus NH2OH hydroxylamine in the presence of H plus first becomes oxime. So R dash C double bond N and OH. Now this oxime can be either syn or anti. So syn position or anti. Okay. It depends upon whether you keep it in a syn form or an anti form. Accordingly, the product you will get. So if you keep it this way and treat with any Lewis acid, then we expect that this R dash will combine with this nitrogen here, right? Nitrogen where it gives away its lone pair to this. So what do we get? R dash N triple bond C plus here, right? Sorry, triple bond C plus here like this. Okay. Um, Not lone pair here. I'll just show the lone pair later on. Carbon plus here like this, plus this one is having R group here. Like this, it will get migrated. Okay. And once you get this here, this is called anti-migration. Anti-migration. And once you get anti-migration, you do hydrolysis on that, we'll get this as RNH2 and RCHO. That's how you can end up getting aldehydes. And first, let me write an amide form first. R dash NH C double bond O R. This is an amide form. And amides, if you hydrolyze further, H3O plus, and slightly heat, then you'll get RNH2 plus RCOOH. These are the products which are formed. Usually, questions you will expect to stop at amides. You're always expected to stop at amides. I have given you a number of questions on Beckmann's rearrangement. I would like you to, go and check that reaction once. Okay, that reaction sequence cases are important. Okay, what is left is one important form, which is acetal formation. Correct. Acetal, and then we have reactions of aldol, canisero, as well as oxidation. Okay, these three, along with tautomerism, obviously, that's a part of tautomerism is a part of that theory. So tomorrow we'll discuss all of that. But meanwhile, in the assignment, you can complete all the preparation-based reactions and reactions up to amines. Got it? Whatever the reactions which are taking place up to amines, you can finish them off. Here.